All right, here's the situation. You get a call. Discharge pressure is all over the place, flow has dropped off, vibrations climbing, and yep, that mechanical seal is weeping again. Sound familiar? These are the classic symptoms.
So before you even think about grabbing a wrench or ordering a new part, there is one rule, one guiding principle for all pump troubleshooting. You have to place the operating point first, period. Okay, so here's how we're going to break this down. We'll start with symptoms and the system reality, then look at the pump internals and the operating point itself. After that, we'll cover the 6 key measurements you need, the 5 most common failure modes you'll run into, and then we'll walk through a real-world case study. We'll wrap it all up with a field troubleshooting checklist you can actually use.
So, let's get into it. The first thing you have to understand is that most pump failures, well, they aren't actually pump failures. They're system failures. The pump is almost always just the victim, the messenger, reacting to a problem that's happening somewhere else in your process. Yeah, the real root cause is almost always some external system change, not that the pump's internals are just worn out. You know, things like suction levels drifting over a shift, strainers slowly getting clogged, or maybe you've got a tiny bit of air getting sucked in through a leaky flange gasket upstream. It could even be a change in control valve strategy that someone made ages ago. The pump doesn't know the difference. It's just trying to respond to these new conditions it's being fed.
So to figure out why the pump is responding the way it is, we need to quickly go over its fundamental behavior, just the basics that matter for troubleshooting.
It really comes down to 3 key functions inside the pump. First, the fluid gets pulled into this low-pressure zone right at the center called the impeller eye. Then, the impeller spins and its vanes sling the fluid outwards, adding a ton of kinetic energy, basically velocity. Finally, the volute, that snail-shaped casing, takes all that velocity and converts it into pressure. That's it. Low pressure in, high pressure out.
Okay, this is the core concept. A pump's capability is shown on its pump curve. That tells you how much pressure or head it can generate for a given flow rate. But it doesn't operate in a vacuum. It's pushing against the system's resistance, which has its own curve. The actual operating point is simply where those 2 curves cross. And here's the critical part. Any change you make in the process, opening a valve, a line getting fouled up, that shifts the system curve. And when the system curve moves, so does the operating point. That changes everything about the pump's performance and how it's being loaded.
So, how do we find out where that operating point actually is right now? Well, to do that, you need to collect a specific set of data points from the field.
And here they are, the 6 essential measurements you need: suction pressure, discharge pressure, flow rate, rotational speed, the temperature of the liquid, and the motor amperage. You need all 6. If you're missing even one of these, any diagnosis you make about starvation or runout or instability, it's really just a guess.
Okay, once you've got those 6 measurements and you've placed your operating point, now you can actually start to diagnose the most common failure modes you're going to see out in the field.
First up, air getting into the line, or vapor lock. The symptoms are pretty obvious. The pump might lose prime, the pressure will be all over the chart, and it'll just sound wrong, noisy. So where do you check? Start at the suction source. Is the tank level okay? Then, you got to walk the line and inspect every single flange gasket and valve packing upstream of the pump. A really common piping mistake is having a high point in the suction line where an air pocket can get trapped. That's why you always want to see a constant upward slope to the pump. Now here's what not to do. Don't just assume the pump is bad before you've checked that entire suction line and made sure it's absolutely airtight.
All right, number 2 is a suction restriction. Here, you're going to see low discharge pressure, low flow, and again, noisy operation. The field check for this one is usually pretty simple. First, is the suction valve actually fully open? You'd be surprised. Second, check the differential pressure across the suction strainer. If you've got a high DP, it's clogged. The fix is obvious. Clean the strainer, open the valve. And the big what not to do here is this. Don't try to fix it by throttling the discharge valve to get your pressure up. All you're doing is starving the pump even more and completely masking the real problem.
Number 3, cavitation. You'll know it when you hear it. It's this loud, crackling noise, like you're pumping marbles or gravel. What's happening is the pressure inside the impeller eye has dropped so low that the liquid is actually boiling. These little vapor bubbles form and then collapse violently as they move to a higher pressure zone. It's incredibly destructive. To fix it, you have to increase your net positive suction head available, your NPSH. You can do that by raising the level in your suction tank, lowering the liquid's temperature, or sometimes by reducing the flow rate. But please, what you must not do is just let it run like that. Sustained cavitation will tear an impeller apart.
Okay, failure mode number 4. Operating way too far from the best efficiency point, or BEP. The classic symptoms here are chronic high vibration and just eating through seals and bearings. When you operate outside that sweet spot, the preferred operating region, you get high radial loads and internal recirculation that literally bends the shaft with every rotation, causing those mechanical parts to fail early. So use your 6 measurements. Find your operating point on the curve. Is it way off to the left? You might have a downstream blockage. Is it way off to the right? You might have a system leak or a bypass valve that's open. The key takeaway: do not just accept repeat bearing failures as a fact of life. Check the hydraulic operating point first.
And number 5, installation-driven mechanical issues. The symptoms here look a lot like the last one, chronic bearing and seal failures, even when the hydraulics seem to be just fine. The field checks here are all about the fundamentals. We're talking laser alignment, checking for soft foot under the pump base, and checking for pipe strain. A great way to check for pipe strain is to disconnect the flanges and see if the pipes spring apart. Oh, and of course, verify you've got the right lubrication. Now, the absolute what not to do for this one is critical. Do not do a precision alignment until you've fixed any soft foot and pipe strain issues. A perfect alignment means nothing if the base or the piping is twisting the pump casing out of shape.
All right, let's put all this together with a quick field example to see how this plays out in the real world.
So, there was this system that was just plagued with problems. Chronic seal failures, really high vibration, and the discharge pressure was unstable. So the team went out, took the 6 key measurements, and what did they find? The operating point was way, way out to the right on the pump curve. So they did a walk down, and sure enough, a bypass line had been left cracked open. This tanked the system resistance and caused the pump to run way out on its curve. The fix was simple. They closed the valve. That moved the operating point right back near the BEP. And the results? The discharge pressure immediately stabilized, vibration dropped back to normal levels, and get this, the seal life went from lasting just 2 months to over 18 months. The pump wasn't faulty, it was the system.
And all of this brings us to a final, structured checklist you can use in the field.
Now, the order you do these checks in is absolutely critical. First, always start at the suction source. Check your levels, check your venting. Second, confirm the suction flow path is actually clear. Are the valves fully open? Are the strainers clean? Third, you have to go get the data. Measure and log those 6 key parameters. Fourth, use that data to place the operating point on the curve. Then, and only then, you start looking at the hydraulics. If you think it's cavitating, try temporarily reducing the flow and see what happens. Inspect the suction piping for any air ingress points, and confirm your minimum flow protection is working. And last, if you have repeat mechanical failures, then you check the mechanics: alignment, soft foot, and pipe strain. You see the pattern? You start at the system and you work your way methodically toward the pump.
It all comes down to this. Remember it. If you can't place the operating point, you're guessing.